So BST and after we are done with the project creation, we'll add two files, bst.h, bst.c. Same approach we'll use for binary search tree also. And BST is generally better for search. We talked about that, right? Search in BST is log n. Every time we divide the search space into half. And the binary search in a one-dimensional array is built on the concept of binary search tree. We jump to the middle and we assume that's the root. If element is lesser than that, we have to search in the left array. If element is bigger than that, we have to search in the right array. So all done. Header and C created. So now we have to define here the structure for our binary search tree. So today it will be a question answer session. Anisha, how do we define the binary search tree structure? Okay, struct, then let's say BST node, because this is a node. Then we'll take root. Right now we are defining just the node. In node, what are we going to store? Data. What should be the data type of that? Yeah, so let's do an element type and call it data. And element type will be a type def. Let's make it of type int for now. So when we deal with this, clear? Int is type def to element type. So data. Apart from data, what else? Yeah, we need to store the left child and the right child. So what should be the data type of left? So left is a member. Can I write VST node like this? This is correct? Okay. Star, because we are storing the address. Same way, BST node right also. Can we write? Yeah. If we are using the name of the structure, then struct keyword has to come along with it. But if we want to write this kind of notation, then what we have to do? Type def. So we'll go with the type def approach, because that we have done so many times till now. Struct BST node, capital BST, or B we can take capital. And every time we use, we'll use capital. So there is a difference between small BST node that whenever we use, we have to use with the struct keyword. Capital we can use without it. Let's make ST both capital. That will appear better. BST node, BST capital. That we will do in create node. Because whenever we are allocating for a new node, we'll set all the variables of it. Data, left, right. So here we don't initialize it. Because here we have just defined a new data type. All done. So what is the first function to write here? Create node. If you want to create a node, so let's write create and call it create BST node, because we have seen, like previously we created a library with linked list tag queue. Tomorrow if we add tree also to that library, then there will be a conflict. Create node is there in linked list also, so there we should name it create linked list node. Here create BST node. Input parameter, what will create BST node take? Data. Shall I write int data? Element type data, because we want to make it very generic. Return type, what will it return? BST node star. Yeah, because we want to allocate a node and we want to return the address of that, and semicolon in the end. But this function we will never call from main. This function will be internally used by insert. So that's why many a times this kind of function people don't write in header file. Though we will implement it in .c, we could have removed it from header file, because if we put in header file, then main can see the signature, main can use it. But for now we will go with this approach. Just be aware of it. Any function that we don't want to give to client who is consuming our library, we can skip that function from header file, because stdio we can see. There we can see what are the functions available. If we hide some of them, and same concept we use in object oriented also. Things we want to hide, we make them private. Okay, so create BST node is done. For insertion, what should be the function? Insert left child, insert right child. Last time we did that. Can we have an insert left function in binary search tree? If root has 5 and I am passing 10, I say insert left child as 10. Can we do that? No. So that means binary search tree is simplified there, because the order of insertion is already defined. We don't need those generic functions. The ones that we did last time, it was a tree which does not have any property. So here insertion is only one function. So insert BST node. We are inserting one more node to this binary search tree. Now what should be the input parameters? Data, the data with which we want to insert a node, and root node. In which binary search tree we are inserting, because our code can use more than one binary search tree. So first we will make it BST node star root, and second we will make int data. Second should be element type data. So this way we write our insert function. Now what should be the return type of insert? It has taken two members, root and data. Return type BST node star, because when we are inserting the first element, root has to change. Though after first element, root will never change, because in binary search tree, if the number comes bigger than root, we go to the right. If it comes smaller, we go to the left. If same number comes again in binary search tree, for now we will not insert it again, because that will violate the property that we have defined. If same element comes, it is already there, we don't do insertion. So return type is BST node and star. So apart from it, let's do two more functions. We want to write a function of search. Given a data, we have to tell whether the data is there or not in the binary search tree. So search BST node, that is the function name we are giving. Okay, I'm input parameters to this root, which is BST node star, then data, the element that we are data that we are searching. So element type data. What will it return? Boolean. Yeah, one possibility is we can return a boolean so that we tell it is found or not. But if we return the pointer of that node, then caller gets two advantages. It can check the pointer. If it is null, it knows it is not found. Or in many cases where we would want to access the node, because in real world these nodes are complex. Here we are putting just one data. Imagine if it is our phone book, there will be multiple members in that. First name, last name, this. So if we are searching for a person, we want to access other members of that. So if we return node pointer, that is better. If we are searching for a node and saying has BST node, then we can return bool. So here what will we return? BST node star, because it serves two purposes for us. And one more function, delete a node. If we tell go and delete node 5, that also we want to add. So what should be the signature of that? Delete BST node, input parameter. Prashank, delete BST node. Root and data, BST node. So all the functions apart from create BST node, they take root and element type data. And what will it return? It should return node. Why? Why not void? Because so question we are asking is whether it should return void or it should return BST node star. And whatever you say, you have to defend it.
BST star.
Why?
If we delete the root node, then next.
If we delete root node, then root is changing. How will we communicate that back? That's the point. So Ajay was saying the same thing but not clear. Next. What is next? In binary search tree there is no next. There is either left or there is right.
I mean next node, sir.
Yeah, I understand. Your point was correct that next node has to be made root. Either it is left or right. So these are the important functions. If we are done with it, then probably we'll be comfortable with BST. And traversals we'll do separately. Recursive traversals are easy to understand, we know that, right? But we'll also do iterative traversals. In order, pre-order, post-order, all of them we'll do iteratively. And then there are more functions that we could have gone about. We can say destroy BST. Given the root, destroy the complete tree. That means free each and every node. Is a given tree BST or not? That we talked about, there is a problem like that. That we will cover separately in interview questions. So for now, these are the functions you need to implement. So you can code. You can start coding these functions. Okay, before you proceed, there is one more thing. In Google Drive, I have uploaded a file, print binary tree. So what it does is, let's say when we insert 5 elements in the tree, first we have to draw on pen and paper to say this is what my tree is. Then we go about delete, because it becomes hard to visualize in case of tree. So this is a file which has an implemented function for printing the tree. On console we will be able to see a tree with left, right children. This someone else has written, we will be using it. Because there it is, how many spaces to print between two children, all that logic is there in this. So once you have implemented your logic, and if you want to see after 5 insertion whether my tree is looking correct or not, you just download this file, or let's do it now. I'll show you, then you can follow this. So I have downloaded this, and you can see it has come to downloads folder, print binary tree. So I'm cutting here. On desktop I have created BST here. So just go to that folder and paste your file. Fine. So now we have one more file added to our project folder. Now we need to include that in our project. The way to include a file is right click here and say add files recursively. That means if there are additional files in our folder, add them. So I click here. By default it will always have our project selected, BST selected, so we don't have to change anything. You can remember shortcut is 3 OKs. First OK, it is selecting all the files if you see in the project. Existing also, new also. New is the last one. Second OK and third OK. So whenever you do right click add files recursively, after that 3 OK you have to press and it will be automatically included. And in this there is a function in the end, print ASCII tree. To that we give BT node and it prints that. So that we'll see once you have done with the code, then we'll see how to use it. Fine. So start coding your first function. I'll also code. Yeah, so what is the first thing to do in insertion? Create node. Is that necessary in all the time? What if the node is already there with that data? If in BST there is left is 1, root is 2, right is 3, and we say insert 2, we talked about we will not insert it again. So that brings one more complexity, that every time we don't need to create a node.
For search and
Search for that what is being inserted.
Yeah.
If it is not there, it will insert. If it is
Yeah.
if it is
Correct. So that optimization we can bring later. We'll add a search call first. For now we can proceed. We can imagine that call is already there. So let's do node, create BST node, and we are passing the data to that. Now where to insert it? Has someone written the logic already? You have written? Okay. Yeah, tell Ajay. We'll start with your logic.
root arrow data
If root arrow data
less than
less than
node arrow data.
node arrow data, if root is less than this, then
Then root of right equal to node.
root of right equal to node,
Else
else root
root of
of left equal to node. This way. And then what do we return back? We have to return the new root, right?
yes, sir.
New or the unchanged root. And say return root.
First we are assigning
First we assign.
root with any other way.
Okay. But are we changing root anywhere in this logic? Root we are not changing, right?
So no problem.
No problem. Okay, so let's trace this function now. Initially, let's say we call this function with the data 2. So right now our tree does not have any node. Fine. So if we call it with 2, root is null, data is 2. That is the function call. So this is null. Here we are passing 2. first line, what will it do? It will create a new node which will have 2 as data. Left will be null, right will be null, because that is what we have done in create node. So this line is done. Now we come to this check. What is it checking? This is null dereference, so it will crash here. First mistake. So how do we fix that mistake so that it does not crash? So what if root is null? If root is null, we return node, because that becomes our root. This was simple. So now we have fixed the first problem. After fixing this, let's try to trace it again. So first thing that has happened is a node with 2 and nulls is created. So now at least we have root pointing to this, and we want to insert a data. So now we are calling this function second time, because first time when we call a node will be created, that will become the root. In main we will assign root is equal to insert BST node, and after that we make a second call with root and 3. So now we have to check what is the flow, whether this will work fine or not. Yeah, all done or working on it. So how many of you missed this check, root null? Only you missed? You also missed? Okay. So in case of binary trees and binary search trees or even linked list, always remember this is a special case of checking. In linked list, the special case is checking the head is null or not. That also we ensured when we wrote the insertion logic. If head was null, return the node. After that, do the logic. In binary search tree also, that is an important case. Now we are calling it again with root as 2 and data as 3. So let's see what the logic will be. First it will create a new node with 3. Okay, so a new node is created. So right now you have node in this and root pointing to 2. These are the two things you have. This is node. Then we check if root is null. Is this condition true? No, because root is pointing to a valid node. So we come to this condition. If root data is less than node data, what is root data? 2. What is node data? 3. Is this condition true? No. Then what we do? We go to else part. Root of left is node. What are we doing? Oh sorry, root of data is less than node data. Yeah, root of data is 2, 2 is less than 3. Okay, sorry. So we should go to if part. So in if part, we are running the statement root of right is equal to node. So root of right, this points to node. So 3 gets inserted on the right side of 2. And after that we will be returning, in the end we are returning root. We are returning the same 2. And root we have not changed anywhere. Right? So at least in this case it is working. Now let's take one more case. And one more case is, now if you have a tree which represents like this, 2 is there, 3 is there. Now we are inserting 5. So if we come from top, we are creating a new node with 5. We are checking if root is null. Is root null? No, because root is pointing to this. Then we are checking if root data is less than node data. Node data is 5, root data is 2. Condition is true. If this condition is true, what are we doing? Root of right is equal to node. Root of right was pointing to 3 earlier. Now we are saying this should point to 5. What did we do? We lost reference of 3. Now we don't have any pointer to 3. So code is problematic, because in this code we have assumed we are inserting just one level ahead. but it is possible that we have to go 2-3 levels down to insert the node. Like in linked list, when we were inserting the last node, we had to traverse till the last node. So here also we have to write a loop so that we find a node from which our node is either bigger or lesser, and left of that is null. So if we find a node from which our current data is less and left of that node is null already, then we can insert. So can you convert this logic to incorporate that? Now that is a problem that we have to fix. Once that is fixed, insertion will be done. So think about it.
BST node start time.
Okay, BST node star temp equals root. Okay.
So that is new.
Okay, here it is correct only. Then here BST node star temp equals root. Okay.
While temp not equal to null.
While temp not equal to null,
If temp of data greater than node of data.
rather than node of data, can we use data here? Because that's the easier way. Yeah. If temp of data is greater than our data, then
If temp of left equal to null.
okay, in this you are saying if temp of left equals null
Temp of left equal to null.
equals
Node.
node,
Return node.
return
Root.
root. That is both in if, right? Okay, otherwise
After that, temp equal to temp of left.
here
Yes.
okay, then there is else,
Else.
similar logic in else,
Yes.
but this time for
Temp of left.
right. If temp of right is null, temp of right is node,
Node of return root.
no need of returning root here, because somewhere it will reach that condition. But if we comment it out, let's see whether. So code blocks will say that your function is not returning anything, because code blocks without running it cannot tell like you are returning in all the cases. So for that sake we can put it, but we know it will never reach in this line because we'll return it. So is this logic clear to everyone? So actual goal of us is we start from root. If the data we are inserting, if that is bigger than the root, we know we have to insert in the right subtree. But rather than making a decision of inserting, we have to find a node. We have to come here now. This is our root, new root. We have to insert in this tree. If our data is bigger than even this, we have to go through the right of this. And any point if we find a node whose right is null, we know there we can do the insertion. If this right is null, we can insert here. And if this right was null here also, we could have inserted here. So we have to go one step down in each iteration and find the right place for the node to be inserted. Now if we compile it and run it, and this is our binary search tree. So here all the insertions have happened, and we can see it meets the property of binary search tree. That is a good enough validation that this is correct tree. Now another thing is, here if temp of data is greater than data, here we could have removed return, and at this stage we can say break. Here also we can say break. As soon as we find a position of this, we can break out of the loop, and in the end we are anyways returning root. So that is one more change we can make to it. Now done for all. Sai. So since binary tree, recursion goes with binary trees, general the way binary trees are written. So let me add one more function signature here and call it O. So I'm just copying the insert and pasting it here, and let's call it R insert. R is for R is for Rushank, correct. R is recursive, because we are going and implementing a recursive version, and you will see how small code it will be. So we are implementing R version. So in recursion we said recursion is always about, if it knows the answer it will do the work, if it does not know it passes on to its child, right? So here also let's use the same strategy. We are creating a node. Okay, node creation also let's skip for the time being. So tell me, if root is null here, that's the base case of recursion, can we implement it directly? Can this function called tell what to do? If root is null, then we should be inserting at root and we should be returning that new node, right? So can I simply say return create BST node of data? Is it fair? Second case where we are confident is if root of data is less than data. What does that mean? Root is less than this data, then this should go to right side. In this case, okay, there is one more check we have to put, and root of right is null. Only if these two conditions are true, we can insert it as a right child. So what we can do, root of right equals create BST node of data, correct? And what should we return in this case? This is clear that we have inserted in the right, because in recursion we know answer in this case also, we are 100% sure. Even if this condition is not true, we check the other condition. If root of data is greater than data and root of left is null, then we can insert it as a left child. This case also we are sure. In all other cases we are not sure, because we don't know how many levels to go down. So what should we do? If none of the cases it enters, that means it will not return. So here we can say if root of data, again we are putting a redundant check, is greater than this data, then it has to be inserted in left. So we say call it recursively and say R insert BST node root of left comma data. Go to the left subtree, insert there. I don't care how you insert. And after inserting whatever is the new root, return me back. So that we put in root of left, because root of left can change with this. Is this clear? Else we say root of right should be changed with whatever right subtree says is the insertion. So we have made two recursive calls. Wherever we were sure, all of them we have made base cases. And now we can reduce the code of our recursive function also. Let's say we don't check for root of right, null here. Can we directly say this logic? So that means I'm talking about removing these other conditions also. So what we are saying is, since I have commented, let me remove it for now. If we had only this much code written, and in the end we also have to return roots. If we have only this much code written, will it work or not? That is what we want to validate. Fine. So let's try to see. with the example that we had taken earlier. Insert 3 first, then 5, then 7. Let's go with that approach. First time when R insert is called with 3, what will happen? Root is null. 3 is the first node we are inserting. So it will return 3 as a root. So this becomes the root now. Second insertion we are doing of 5. Root is not null. It will go to this. Root of data is greater than data. Is that true? In root we have 3. Now we are inserting 5. This condition is not true. So we go to else part. And we say root of right should be updated with insertion in the right. What is the root right now? In root we have only 3. Root right is null. We are making a recursive call with that. When we make a recursive call with that, when root is null, what does it do? It creates a node and returns back to us. That means 5 will be created and returned to us. Now whatever comes back, the function call returns here. What we are doing with the return value? We are updating root of right. This will be updated. So root is sure, root says only if I am null, I will create a new node and return you the node. Now it's up to you, where do you want to put its address. Now if we insert 7, let's see, if we insert 7 into this, 3 is there, 5 is there, 5 is right child of 3, and we are inserting 7. First call, here we come, create BST node. This will happen only if root is null. Our root is not null right now. It will go and check root data, is that greater than our data? We are inserting 7, it's not greater. So what we do? We call root of right is equal to recursive call we are doing. We are saying recursively insert in this tree. If it is inserted here, our problem is solved. So this recursive call happens at 5. Again it goes up. Now 5 becomes the root. Because here we are passing root of right as root. When recursive call happens, that is not null. Root of data is greater than data. Is 5 greater than 7? No. It goes to the else part again. In else part, it passes right of this, which is null. It passes that as a root, makes a recursive call. Null 7. A new node is created, that will be returned back. And right of 5 will be pointing to that. And in the end, we are returning root. In previous function call, 5 came as a root. 5 we are returning back. When 5 goes back, then it comes back to previous function. That returns pointer of 5 that we assign to right of 3, which is the same. Earlier also it was pointing to 5, now also it will point to 5. So in recursive, if you see, with just these many lines of code, we have written the logic. All the other 2 checks that we included, they were redundant. They were not required. Even if we put them, then also this function is doing a lot of things, but that is not needed. So I'll leave that also for your reference, because this code I'll upload to the drive. So this is not required. So we have seen both recursive variant and iterative variant of insertion.